All right. So today I wanted to talk about the final. Instead of doing like a big, can you recall, time your coding kind of thing, you can do that with go work for Google. He was thinking I could take well paper. You all will have to read research papers. You either have read research papers or you're going to read research papers. And so get a little better at that. So class, here we go. So we had a bunch of these goals here at the beginning of the semester, if you can still remember. And so a lot of it was about data and model quality. And so this is what we've been talking about. This is where all these Jupyter notebooks are for. But you're going to get your model from somewhere. You're going to get your data from somewhere. And that is going to be described in a scientific paper. And that's basically this final paper. So I want that in my email box. We have an official class final time. Like that's when I want this in my email box so I can start grading. It doesn't need to be long. I just want a couple of questions answered. And so that's what we're going over today. And I've got two examples. Hey, ones that I wrote because I know where I put the answers. And so really this is it. That's what I'm talking about. And this week I want you to pick your paper. There are two ways to pick your paper. I'm already working on a research project with Professor so-and-so, and they gave me a paper to read. There's your paper. Perfectly happy to double up on the work here, because then you can go, well, hey, I had to summarize it for this class. Now I have to read it, right? Now I have to parse it apart. The other one is I have a list of papers in this week's Blackboard. There's a folder with a bunch of papers. Title, abstract, pick one. But you need to let me know which one. You go like, yeah, I want Turner 2021. They're all from the last month. So these are all papers that I went, ooh, and I haven't actually read them yet because, I don't know, I just go, ooh, and then forget about everything that existed. So I see it. I want to go read it. I think these are interesting. And so if you say, hey, I want to go read that, then you're making me read those. So we can go compare notes. If your semester at this point is starting to resemble Calvin's desk, let me know, because we can work something out. I really want to reiterate that. This has been an interesting year. So we were going to have some give me some movement, some wiggle room if you want me to help you with that. So for the final, we just do a paper where you either pick out the visualization. You go like, oh, I really love the way they plot this, right? How they actually convey everything in one plot. But I want you to give me context. So you need to actually pick the paper apart. Strengths and weaknesses are really like the obvious question that comes up. Like, what's the strong thing about this paper? What is really convinced me that this was true? And where's the part where you not only raise your eyebrows, but like, I don't, that moment. So both of those, there will be strengths and weaknesses. If it's a good writer, they'll have hidden the weaknesses expertly, and they'll show off their strengths at every turn. That doesn't mean they're not there. And so you can summarize as well. So we're going to skip the presentation. Usually I would prefer to do this in a presentation, because one of the things that you need to learn as a scientist is take your data, take your result, or take somebody else's result, and give a 30-second, 60-second, 5-minute, here it is, right? Just convey what the importance is. So we're going for paper, but short. Shorter definitely than the paper originally. So there's your word limit. You cannot go on longer than the paper itself. That would not be a summary. Quite a number of the paper have at least some sort of machine learning thing in the actual title. So those are the papers that I put in there because I'm kind of curious what they got. However, if you have another paper, you have a paper that's like, yeah, look, I'm doing this for a research project, so I already have a paper that I need to read. I'm happy to suggest these, but these are all astronomy papers. Not all of you are astronomers or even aspire to be astronomers, so that's fine. It's just that these are the ones that I can follow along. So if you have something that you want to explain to me in physics, you might want to use smaller words because you're just talking to an astronomer. But see if there's anything about machine learning that you would like to talk about. So it is the kind of thing that I want to then critically analyze, right? So there's a bunch of these machine learning titles in there, and we're not going to just go like, oh, they used magic, right? As soon as you replace machine learning with magic, and you can use the exact same phrasing throughout, you haven't explained what you've been doing, right? I waved a wand, and then the data said this. That's not what we want. So if you look at a paper, you want to know what the main conclusion is. If it doesn't have one, it's not particularly strong paper, right? Most of the time, the rule of thumb, remember everything that I say is a rule of thumb here. The rule of thumb is that you have like one result, one paper, because then you clearly can work towards like, here's the thing we found. What's the strength of the method? So if you go, this is a perfectly matched data set to this kind of methodology. If their methodology is clearly explained. The methodology section of the data sections in papers are duller than watching paint dry for many cases, because it's the thing they had to write, and just the energy from, I had to write this, just kind of comes off as well. Yet, you can identify what the strength is. They should actually mention that. We chose this particular method because it's well suited because of A, B, and C. That should be in there somewhere. What's the weakness of the method? There are a good bunch of authors that are good scientists that go like, look, we are aware that the Kolmogorov-Smirnov test cannot be applied in all these situations. We're aware that k-means clustering can only be done in like nice circularized clusters and not in elongated ones. That's bad, right? So that's the kind of thing where they actually identify their own weaknesses and goes like, well, we're aware of them. We don't think they're going to be a huge issue, but we're aware of them, so you, the reader, should be too. What is the context? Like, this is the biggest question for me. Why are these people even doing this? Every scientific paper is a significant effort by students, staff, faculty, postdocs, technical staff, money, computers. A lot of effort went in it. Why did they do this in the first place? What motivated that? There should be a sentence, and oddly enough, sometimes authors forget this, to put in why they're doing this at all, because it's so obvious to them that, yeah, I haven't put it in there because, obviously we need to do this. So you're so down the well that they forget to put this in. So look for it, right? If they don't put it in, go like, why do you think they did this? Is the result well illustrated? Honestly, there's another pitfall for scientists. It's hard to make nice plots. It's hard to clearly communicate using visual means. So is it convincing? Is it convincing you? Is that the main plot? And then especially for these last two are for machine learning. Does it scale to new data? So suppose this is kind of typical. You do a survey with a telescope. You take like a big chunk of sky. You take a picture of all of that. And then you use machine learning on that to classify what you saw. That's great. Well, suppose I move my telescope to the southern hemisphere and do it again. Could I do the same trick? Is it still usable? Or did I use all the data? There is no new data. And this is something that a lot of machine learning people will run into. So there's like, I did this fantastic thing. I showed that it worked. I used all the data. And there's none forthcoming. At which point you go, so why did you develop the algorithm? Because now you have an algorithm that has no market, that cannot do anything for you. I mean, it might have done something once, so maybe that's enough. But is there any new data, and can you actually go apply that to that? And is it ethical to use it, right? So that I find this is a question that is posed more and more often, which is that, okay, what have you developed? And can that, everything can be used for malicious purposes, right? But the purpose that you made and the purpose that are readily adjacent to that, are those ethical? Is this a good use of this data, or is this something that we should worry about? And so those last two are bonus questions. You're all kind of like, I don't know how to answer this stuff. Like, okay, that's fine. They're bonus questions. But especially for the machine learning stuff, I want you to look at the scale. Does it actually have a market? Does it go somewhere? And is it ethical to go there, right? Because a lot of this machine learning stuff, facial recognition is now so good that it's a little terrifying without a mask on. Is it ethical to use medical data in how to use it, right? There's a whole subsection where you need to ask for special ethics permission if you're doing any kind of, if any personal information is in there. Meanwhile, everybody happily chucks all kinds of personal information online. You can scrape it. And so, yeah, there are machine learning tools for that. So what's ethical and what isn't? And so I love to hear from somebody, I don't know, maybe I have a philosophy major here. I'd love to hear what your take on it is. And if not, we're all physics majors, so we're all going to be good at this stuff anyway. So I want to have your take on it anyway, right? So, okay, the conclusion is what we start first. It's almost like writing a paper. So you find their conclusion. It should be in the abstract. If it's not, it's a bad abstract. And it should definitely also be in the last section of the paper, not the bit that says acknowledgements, you know, thanks for mom and dad, my pet rabbit. It's the one above that, right? It's the one that says conclusions, concluding remarks, blah, 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 blah. We think this. So you should distill that down to a 30-second conclusion, right? There should be something where I'm pushing a button, you jump into the elevator with me, and you can say, this paper found that. That's how short it should be. Old school tweet you should think of, 180 characters. So it should be in the last section and in the abstract. If it's not in, like, you should be able to find this. If there's no clear conclusion, what kind of paper was this? Right, so this is a first test of quality. Can I immediately, you know, it's like a litmus test. Everybody here knows what a litmus test is, yeah? I don't know how much chemistry you all get. So it's the first test that you do for a paper. Like, can I find this thing? Because if not, why spend the rest of my effort on going through, you know, line by line later? Okay, the very best plot in the paper probably should support that said conclusion. So we spend different amounts of time on different plots. I spend a lot of time making this one plot just right, to just make it very convincing and cuddly colors and like easy to read and all that stuff that I've been talking about, how to visualize data. There's always one plot or one or two plots that support the main conclusion. So those have to be perfect, right? They have to be, throw it up and everybody knows what you said. Okay, so that's the conclusion. You first find the conclusion, then you find the strengths. Is it a new method, or is it a really new application? Is there anything new about it? I'm actually training you a little bit as if you were the referee. Because as soon as you are a PhD student, you can be the referee for a journal. The minute you are in their databases, they're going to go, oh, this person knows about this. Excellent. Here's a paper about that. Can you tell us if it's any good? Because if you're the editor, you're kind of like me. Like, you have some general knowledge. You have some specific knowledge, but you have, you know, sort of fine knowledge everywhere, which means I can find a person who actually knows about it. The editor is not the expert. The editor is who knows the expert. And so you go and find somebody who can say, hey, what are the strengths? Is this a new data? Is this new method or new data? There has to be something new in here. Is this really needed? Right? Sometimes it's like, yeah, actually, this was kind of floating around in the literature in like 15 different papers, and we all pulled it together, and it's now in a neat little Python packaging. You can all use it, and nobody has to do this as a headache anymore. Honestly, really welcome papers. Nothing new there, but something that was sorely needed. That is also good to have. And preferably a use case. So if you, for example, you introduce a new application of machine learning, this is what you would use it for. Because if you just go, this thing is 15 times more efficient, to do what, right? So that's what I want to know. So you need to know the strengths of the paper. Like, you're going to sell this paper. You have a referee. As a referee, you have to go like, okay, these are the strong points. Excellent. And then you also go through it and you look for the weaknesses. Weaknesses are bad rationale. No good reason to do this. Maybe there was, but they didn't quite. They go like, yeah, there's, they sort of got going. There's missing or misinterpreted data. So it's just like, as you can see in this figure, and the figure doesn't exist, for example, that happens very rarely. However, often, and I have to hammer on this with my colleagues, and when I'm a referee, I'm going like, all right, well, you got to put the data table in there, because I should be able to reproduce your results. Remember reproducibility? Yeah, I want that table, and I want to be able to read that in and make my own plot and put my own result on top of it, right? So that's what I need to be able to do based on a paper. Poorly motivated methodology or inappropriate, right? I use the statistical method because it's the first one that came to mind. They won't say that in the paper, but you kind of go, I have no idea why they're using these, or mixing two together or something like that. That's typical of like, I don't know if you thought about the whole method thing here. You just kind of threw it in the nearest SciPy statistical test you could find that didn't return none. So that's not enough of a motivation. And you'll see that, right? I've refereed a paper where I went through and it's like, okay, they're using a KS test here and a test here, and then back to a KS test. And I'm like, how am I supposed to... Why? Why are you doing this? And why is this not in a neat little table? So, cranky referee at that point. Logical misses. If you go like, blah, blah, and you kind of feel like you misstepped on a stairs, that's exactly what a logical miss is. Yeah, wait, how did we get here? That's the thing, you go backtrack, you're like, maybe I just, blacked out about the last paragraph, but probably not. There's something where you go like, they're not taking you along. They're not taking you, the reader, through a logical step. And so if there's a misstep there, you can go, there's something missing here. It could be fine. They just forgot to tell me. And obfuscating is, as soon as you find it, it is absolutely horrendous, because that's not the point of the paper. Again, reproducibility is the point of the paper, right? So I should literally be able to grab your data, know what your methodology is, and reproduce the exact results. So for cosmology, for example, we have this issue that we don't quite know how fast the universe is expanding right now. We've had this problem for a while, but how accurate has now been shrinking steadily for the last 20 years. It's the reason that we launched the Hubble Space Telescope. We got an answer that was no longer within a factor 2. We're now down to 3% errors, which is great. Triumph of modern science. The problem is that it doesn't agree with the cosmic microwave background. So essentially, we have two measurements of the same constant that are not in agreement with each other. If you want to do that, you go basically swap data between the teams, and they do the exact same analysis with their own code, with their own analysis, with their own assumptions. And they basically, yeah, no, the other team did a great job. We're also doing this for Hubble Public, and then recently there was a paper that, yep, we picked different software, we had different assumptions, we went through the whole thing. It's still in agreement with the results that they gave. So people, this is also a motivation for a paper, right? New data, but it is reproducibility and fact checking. Like, so that was not, so if you go back to strength, not new data, but new method. And especially checking an important result like that is really critical to good science, but not like splash something new. Okay. This is the important question, as you can imagine. I had an Italian professor who basically went, why should I listen to you? He also had the gesture down, so he's Italian. But that was like, at some point we just started emulating him. But it was the thing, like, he wanted to hear in a talk, any scientific talk, immediately, why are you doing this at all? So any scientific paper should have that, right? And you shouldn't be Sheldon. You shouldn't be waiting for the motivation until like the 5th, 6th page. Somebody should tell you up front why they're doing this. If they're not, it's like that's a mark against the paper. So I want you to, in a good case, actually be explicitly stated. So find it, or it should be heavily implied throughout the introduction, right? So at some point you should go, this is why they're doing it. By the end of the introduction, you should have that. If not, but also think about it a little in a wider context. Like, why are we doing this, for instance, for the whole field? Why are we doing this for the whole, as a society as a whole? Like, if you kind of go like, yeah, they didn't actually say this, but this would be, you know, invaluable for, I don't know, particle physics, despite the fact that this is supernova cosmology. You know, this is the kind of thing that's like, yeah, this has ramifications. So if you can think ramifications of your own, fantastic. But I really would like you to know, to pick out, you know, actually pick out the sentence that's like, this is the motivating sentence, or this is the motivating section. Feel free to cite the paper, like to copy and paste, grab it here, and there it is. Is it well illustrated? So this is something that you go, yeah, I'm a little colorblind, so I could not tell these two lines apart until I asked a friend. Or you can go, there was no issue. I could read this, you know, from halfway across the room. It was easy to read. I didn't have to read the caption below. I didn't have to figure out where the whole accompanying text was. So is this something that you're like, oh, I'd use that plot in a talk any day, or proposal or something like that? There are people that write fantastic plot papers, and there's like, yeah, I just totally use their stuff. Steal their stuff and go like, look, this is why we're doing it, right? Because the motivation just shines right out. And there's people who make, you know, maybe this was their first time plotting. So I've shown you some of the horrors that I have perpetrated, right? So there's a reason that I'm pointing this out. Does it place everything in context? Clear labeling, like you don't have to go look up what all the acronyms mean. Does it have a good use of color and shape? So these are the kind of things, like there should be a main figure. Copy and paste that main figure. Like basically screen cap it, stick it in your paper and go like, this is the main figure. This is their main result. That's where it is, right? You don't have to write everything down. You can go like, this is their main figure. Look, here it is. You don't have to say their figure 7, because then I have to go look it up. You can just go copy, paste, there it is. So those are the things that I want you to go through. I'll post this on a PDF on Blackboard as well. And so these are the things that you can then go over. And are you convinced? Please tell me that, right? Is this a paper you go like, yeah, this looks good? Or you're going like, I can't put a finger on it, but none of, you know, this is the face you've been making throughout the whole thing. Would you use this result? Or are you kind of going, oh, it's nice, but no? So that's the kind of thing, like that's, I hate to use the word gut feeling, but there is a thing that if you read something, do you like the book? Like some people love this book, some people hate this book. Did you like the book, right? That's the question. And so here's a couple of more questions. So if you get a machine learning one, the first one is, does it scale to new data? So first off, is there any data? Did they use all the data? Did they, oh look, I forgot a verb. This is what I do. Did they use all the data available right now? Or was it like, yeah, we use this on a little pilot program, and you know the data is now coming in and we'll be using it later. So it's like, this is like feasibility study. Yes, this works, great. We're now going to use it on the big survey. Would it be useful? Sometimes, and I feel science doesn't reward this enough, a null result. We tried it. It failed spectacularly. Look, it failed this way. There's no way you can get this to work. Everybody stay away from here. This doesn't work. If you do a convincing job of saying why this doesn't work, why this methodology on this kind of data doesn't work, that's really helpful for future generations. Yet, we don't publish those results. We only publish when we find a result, right? When there's a positive. I really feel null results need to be published more often. And so is it ethical to use? Just because we can doesn't mean we should. Good examples are, oh gosh, anything in using machine learning in medical tech, or hiring. Hiring is always a good one. We've fed our machine learning algorithm the resumes of everybody who works here, And now we're going to hire more people who look exactly like them for some reason, right? So this is a fantastic way to get monocultures, which, if you know anything about plants, is a really bad idea as soon as there's any kind of pest or anything else. Is there ethical uses using this methodology, right? So there are things like shapelets didn't sound too bad, except that you realize that shapelets are a part of facial recognition. Then you go like, well, there are some issues. If I make facial recognition 10 times easier to use because, well, now you can use it on a phone, is that a good thing? And so what kind of issues can you see? Like a little bit, try to look a little further. This is something that a lot of physicists are now are sort of waking up to. It's like, wait a minute, we're really good at it and we're totally technical people who love like, oh, we can solve this problem. That's great. But what is that going to end up being used for? And so you're not completely off the hook once you've pushed it to GitHub, and that's it. That's that. So you need to go. Of course, there's always an XKCD about these things, right? But hiring is a fantastic example. I think a lot of medical use is a fantastic example. And you can be honest and say, like, yeah, this works because we tried it on the development team, and the development team was entirely white. So it works on white skin. There you go. But that's the kind of thing that, for instance, was left out. It was then people say, then it was often presented as if, it works on everyone. It's like, no. You didn't delineate your experiment enough. And so that's another ethical thing. Like, did you actually delineate where it works and where it doesn't? So those are bonus questions because I'm curious what you think. But again, if you're going like, it's the end of the semester, please let me go, that's also fine, right? These are bonus questions if you are tickled by this. If not, please leave it alone. Paper choice. I would like your choice of paper by next Tuesday. You should either have stuff already ready to go because you're in a research project and you had, people have handed you PDFs to go read. Go use that one. You go like, but I already read it and I know what the conclusion is. Great, you're halfway there. Keep moving. Or you can pick one from the repository that's in this week. And they're all astro papers, and I apologize for that. They might be extragalactic astro papers because that's what I do. And I'm not even apologizing for that part. But you pick one, and you let me know. Like the minute you go, oh, that's the one. Oh, yeah, that looks great. There's a few, I think Wade, you might want to, like, there's a few in that you go like, oh, I'm reading that one, right? I was kind of going through and it's like, Dominic and Wade might want those. Cool, that's fine. If you want to have one, it's like, yeah, I already have one. Does anybody else do research like here already, have papers assigned? Does everybody like astronomy? Okay, enough to machine learning to at least read a paper. But let me know which paper you want to do because I prefer if everybody picked a different one. It doesn't have to have machine learning in it, by the way. So a couple of those are simply more traditional ones. But everything that has Bayesian in the title or machine learning or convolutional neural networks, astronomy is taking to machine learning like you wouldn't believe because we've got these new telescopes coming online. And when I'm saying coming online, I mean like they just finished the secondary assembly on the LSST, so the Vera Rubin Observatory. So there's like, yeah, this is in 6 months' time, a terabyte of data at night is coming. So we better get ready, right? That's the level of urgency astronomy is feeling. And a lot of other sciences, Atlas is already there. They're already using machine learning to identify which things to keep and which not. So a lot of sciences are kind of realizing that they're going to deal with more data that they can possibly just look at or have a grad student look at. So they need something new, and that's where the machine learning comes in. All right, so this is one of the examples of the papers. So title, authors, abstract, we've gone over the various elements that you see in a paper, right? So in a scientific paper, they always have the same. It's a very set piece. So instead of literature, for example, where you can have things in rhyme and not rhyme, and you can have something nonsensical as Ulysses, or something as poetic as, well, whatever your favorite book is. But you can tell when people have trouble writing. You can tell when people are like it just flowed out of them, or it just flows right into you. Then it means it's good writing. But the first part of a paper is always title, people who contributed to some level to the paper, their affiliation, so where they were when they did this work, where they are now, and then the abstract that summarizes the paper, the last thing that is written, right? So if you're reading a paper, you start here. You start like you read I typically read the title and then the abstract. I sort of skip over authors because why bias yourself that way, right? So just go straight to abstracts. And then the rest of the paper follows. Usually introduction, methodology, data, results, and discussion. It is so box standard. Those things are in my template now because I always have a section that way. Here we go. So how to read the paper. We start with the abstract. That's sort of like a mini paper. It's hopefully the last thing they wrote because it's the kind of like, well, I've put everything in and here's like the why, the how, and the what we found, right? That's there. Then I typically kind of skip through the whole paper and don't actually read. I go figure, figure, figure. It's like figure 1, figure 2, yeah, there you go. Maybe read a caption, see what they're talking about in the text, but not even that, right? I just go figure, figure. Do I understand what's going on? And then I read the conclusions. So find the key figure, and then I read the conclusions. That's my speed read. Often that's as much as I do. So there are all these fail-safe moments where you go like, okay, the abstract. Oh, wait, they're not doing what I thought they were doing based on their title. They were doing something completely different. Oh, this is not the paper I should be reading. That's when you stop. Or you go, figure, figure, figure. I have no idea what they're doing. Maybe this wasn't the thing that I was looking for. And then you read the conclusions, you go like, well, the conclusion kind of went nowhere. Okay, that's another point where you can just stop. The speed read through is how you can kind of get the feeling if this is the paper you should parse through in detail. And then you go from introduction to conclusions. But you do this, I thought I was the only one, and it turns out most people who are in a field for a little while, this is how they kind of skip through a paper real quick to see like, oh, this is what they found. Later when I have time, never have time, but later when I have time, I'll go maybe do this. And often I go back like, wait, there was this person who did the thing, and then I go find it again, and then I might read it all the way through. So that's how I would suggest you read a paper. So this is the last slide, and then I'm going to go and give 2 examples of 2 papers that I just finished. So you can actually go see what I mean. We're going to go pretend we're the first-time readers. But I do want to actually emphasize that we're doing this in the weird world. So if you are stuck on something, if something is not working, you get sick or whatever, I do want to know so that I can help you, make sure that you get through this class. Next week, we're going to do the machine learning parts. So we'll get to, well, what machine learning is, what people mean with it, big data, what do people mean, whether they, how do we work with them. And we'll start on things like k-means clusterings and self-organizing maps. These are the things that I happen to know a lot of. And then we can go through some other examples as well. So we went from data, we did a model from which we got inferred parameters. We got a level of confidence for those parameters. Then we realized that not everything is a Gaussian, so we used MCMC. So we actually got posterior distribution functions that were not Gaussian, actually had tails and had like real life configurations. And now that we've done that, we go like, well, maybe the model is something that we can leave to the machine to figure out. And so that's how you kind of get at machine learning. Okay, so no idea what time it is now. Oh, it's 6. Okay, great. See if this works. No. Okay, so this is a paper that I just sent into the referees. Hi, Wade, you're on there. title, The Observable Supernova Rate in Galaxy-Galaxy Lensing Systems with the Test Satellite. So there's already a tendency for non-snappy titles within physicists, right? You're already trying to be complete and comprehensive in the title. So typically you sort of end up with a abstract that's the size of a paper and a title that's the size of an abstract. Parsing this together is like, okay, we have a supernova rate in this kind of system and observe with that thing. Here's the authors. The abstract tells us, you know, what we kind of want to know. So here, nope. Introduction, and so notice that this whole thing is always one paragraph. This is one of those rules that are enforced by journals. I often end up going like, here's my 3-paragraph abstract, again, because I'm writing a small paper as an abstract, but it always, all the line breaks and everything get taken out. It's one solid block of text. So sorry about that. That's how this works. But you can kind of see that it goes blah, 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 blah. Here's some motivation. So this is the satellite. We want to see the supernova. We explore this possibility. Let's see if those can be detected by tests. An opportunity to measure the time delay between light paths and constrain the Hubble constant independently. There's my motivation, right up front in sentence number 3. So if you go like, I don't care about Hubble constants, you can wonder away at this point. But you also know like, oh, this is what they're trying to do. That's why. I was very explicit about this in this one. Like, I'm getting more and more trained to go like, oh, I need to actually write down explicitly and as upfront as I can be to say why we're doing the whole thing. Because otherwise, I'm not making you slog through this if you don't care. And then we estimate, we do this. Like, there's our like tiny little method sections. Method sections in abstracts are tiny because, hey, we're getting to the details. That's all later. But the abstract's like, we estimate. How? Read the rest. So motivation, methodology, and then this is already results. The rest, the second half of the abstract is results. So see how that works? You basically have why and what. And the how is in the rest of the paper. So an abstract basically reads as why and what. If it doesn't, and it goes to talk about like the 15 different statistical tests that they ran, where's the why and where's the what did you get, right? And the get is like, well, we get this many, we have this much of a chance, and then you know, put in context, lower than the other existing facilities, but still worthwhile. That's it. You can stop at this point, right? You can go, oh, okay, well, that's nice. I'll go on. Now, if I go through this paper, here's figure 1, here's figure 2, figure 3, oops, excuse me, 4, 5, figure 6, 7, 8, 9, and 10, and 11. Okay, so I want everybody to vote. Like, I'll go through it again. But I want to see if I can actually get this to full screen. Come on. Enter full screen. There we go. All right. So if I go through this paper, so this is kind of typical of how you scan through paper. Here's my first page. We just read the abstract, sort of sped through the abstract. And then you kind of glance over the figures. All right? And I want you to go like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. Just judging from what everything looks and where they are in the paper, what's the most important figure? I'll go like this. Are either of these the most important figure? No, they're set up. Are any of these 3 the most important? No, that's already clear because they're all black and white and they're just like, yeah, here's a distribution. Are any of these the most important figures? Which one of these would be the most important figure then? This one? Okay, I want votes. I want people to hand up, like, is this one the most important figure? 2 votes in favor of that. Is this the most important figure? 2 favors in that. Is this one the most important figure? Or is this one? So it's not necessarily the last figure, right? That's the first thing I want you to take away from it. You're already going like, well, the more color there's in use, that must be the more information I'm being told, right? So you can argue that this or this one is the most for 2 reasons. One, here's the main result sort of summarized in apparent magnitude and how many you can see. So basically, like, here's the test limit. So it's like, oh, yeah, you can see tons of them. However, you can integrate that and compare it into context. So can I blow this up a little bit? Okay. So what I look for when I'm looking for figures, for example, is where do I see lots of citations? Where do I see other people's data as well, where I'm putting it in context with everybody else? See, that's an important figure. Again, there's basically 2 ways that I'm showing the same result here. I'm showing like how many supernova can tests actually find, right? That's the first figure that everybody's like, yeah, that has to be it, right? And yes, sure, that is the main result from this paper. But here's the one where we're comparing the numbers that you can find to the other observatories and show like, yeah, this is the logs of the number per year. So it's like -2. So every 200 years, we're going to find one with tests. There's no NASA mission that's going to last for 200 years. So we basically have a 1% odds of finding one. But notice that the other ones are like, yeah, we'll get 200 a year. That's way bigger. So we're trying to I'm putting them in context to the other observatories in existence. So that's how you can I can identify this is a paper that has been worked on, and like that's the important part. Like that's where we're getting it in context. At least that was my intention. Although now I'm second guessing myself because everybody went like that other figure was the important one. So. But I want you to notice it's not necessarily the last figure. It is the figure where you see lots of other references, or the figure where you go like, oh, wow, they've really kind of like splashed, this is the result. So those are the ones that you study in a little more detail, because inevitably that's what ends up in the concluding remarks. There'll be a concluding remarks part here, conclusions or concluding remarks. So that's the first thing you read. If at that point you go, okay, I got it, and I trust you got it, it's fine. But if it's like, oh, I'm basing my PhD on this, I'm picking this entire paper now apart. But it's not necessarily the thing you need to do then. But you need to be aware that this thing exists, that those values exist. Okay, so that was one. I got you all for a little longer, so sorry, people. So, you enter full screen. All right, same trick. Much longer author list, but different journal, right? So I just wanted to make sure that yes, the layout might be a little different, but every scientific paper follows this principle. You get the title, you get the authors, you get this huge list of like places these people are at, which is weirdly like Savick, for example, here has 4 different places. Well, lots of people have double affiliations. They work at a university, but also at the observatory. They work at, so she works at the Museum of Natural History and at the Community College of New York, right? So these are 2 places that she works at, so she has both affiliations. That's quite normal, but you can kind of see where people are at, so you can maybe later contact the relevant authors. We have an abstract where, let's see how we do this time. So-and-so predicts spectra based on images, we're using machine learning. So this is like, here's setting the stage, right? So the first part is a why. So if you're in Shakespeare, it's when the bard or the bode or the messenger comes on stage and just kind of sets this. There's like a moment where he says, you know, so-and-so, the battle has just ended, because, you know, it's really expensive to put a battle on a stage, so you don't say, you know, it just happened just off stage, but somebody comes up and says, this is why, this is set the stage, right? In this letter, we test our prediction on a unique object, blah, 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 blah. And so after obtaining a machine learning predicted spectrum, we compare it to all existing spectroscopic information that is comparable to a SDSS spectrum, you know, the kind that they predicted for the central region, to archival, one extracted from this thing, and then a new targeted observation. So we also got an observation. Prediction was from this machine learning black box, and now we got spectra, and we're going to go compare the two. So essentially, this is opening the envelope. With machine learning, this is called, I have trained on like a chunk of the sample, and I have given a part of the sample, stuffed it in an envelope, licked the envelope closed, and gave it to a trusted friend, so I wouldn't actually be tempted to open it. And now that I've got my prediction, I'm going to have a look. So that's kind of how this works. I really feel like I'm leading you on, because I wrote these things, so I'm now realizing that that might not be the best way to do it. But that is the entire motivation, right? So here's our motivation, and then result. So it's motivation, result. There's hardly any how, because, you know, that's the rest of the paper. So agreement is quality of the good, blah, blah, blah. The nuclear spectrums equivocally show strong lines in this, lots of spectroscopic talk, and then it's a little weird that this thing has an AGN. So did the machine learning thing do a good job on a rather weird object? And the answer is yes. So can you find, here's figure 1, showing where all these observations are, right? Here's this big galaxy, there's the nucleus. So we took spectra in these things. Okay, this is not helping, because I'm pretty sure there's more figures. There. So figure 1, there's the prediction. The black line's the prediction. Figure 2, this is where we observed it, right? That's where we took our observations. Figure 3, compare the black line to all these different colored observations that are color-coded here. And then compare where the line strengths, so the emission line strengths are, and then also compare to colors based on satellite. We're going to play the same game. What's the most important figure in this plot, in this series of plots? Is it figure 1? I mean, everybody has to raise their hand if they actually think this is the most important figure. So figure 1, no votes. Okay. Figure 2. Right. Oh, figure 3, where we're. Okay, go 1, 2. Figure 4, where we're comparing line strengths. Or figure 5, where we're comparing colors for this galaxy. So we got like 3 votes for figure 3 and 3 abstentions, because you haven't voted. I noticed that you haven't voted. So here's the thing. This is the prediction, but it doesn't show anything else. It just shows examples of an AGN, a quiescent galaxy, and a star-forming galaxy. So you can see that star-forming galaxies have big ionization emission lines. So this is when oxygen and hydrogen are basically being ionized, and then the electron recombines, and you get emission. So you get very clear, strong emission lines. And AGNs do that as well, because an active galactic nuclei is a supermassive black hole. It spits out all kinds of X-rays, so you got ionized gas nearby. And so quiescent galaxies, everything is, there's no hot sources. Well, the hottest thing in there is like the sun, and that doesn't do a lot of ionizing. And so you don't see those emission lines. So there's kind of like, these are the predictions, and this is what we for Rubin's galaxy. So it's important, but it's a setting the stage kind of figure. Then we look at this one and go, yeah, that's, we looked here. Just in case you want to do it as well, we looked here. That's it, right? It's an important point to make, but it's not your main conclusion. Here it's, we compare all 4 spectra. Every circle here is a different observation. So we compare all 4 of them. Not every one of them has the same bandwidth, the same length of spectra. So sometimes it's like, yeah, it just ends. But that's just a comparison. So that's, I think, is a good, pretty important figure. So it's either 3 or 4 where we take the length, the strength of those lines, and see what that compares to the green is the actual observations, the blue is the machine learning prediction, and red is something that we observe with an archival. And so they don't agree terribly well. So line strength is maybe, was like, yeah, that could be better. So both, it's sort of split between those 2 figures, I would say. This one is just a sanity check. Again, you don't have to have the last figure be your best figure. There's often a last one where you're like, oh yes, and in order to make sure that, or then we compared it to, and then we did this, it's like, yeah, we did this one more thing. So that's very normal to actually, at least for me apparently, because I put like one more figure in there. You don't have to, right? I could have stopped here, and that would have been fine. You already figured out that the first few figures are usually not where we put the conclusions, right? It's where we, like, our assumptions are valid, our data is okay, all those things. Those are the kind of figures are up, figure 1 through x, and then x plus 1 is the one that, here we show what the result is. So so this is a letter, and letters are like the shortest punch you can do in physics and astronomy. Letters are 5 pages, sometimes 4 pages. That's their hard limit. There are 50 references. You're not allowed to do more. So suddenly it's like, sorry, people, I can't refer to everybody. And it's simply one conclusion. Did machine learning work here? Yeah, kind of. And so those are the kind of things that they sound like they're fun and easy to write. They're sort of fun, but they're not easy to write because you have to stay within a limit. And everybody who's ever written a paper kind of went like, well, I had to kind of look up some words so that I finally got to the word limit or finally got to the page limit. It's the other way around here. You're constrained by this, and you have to really make your case in a short amount of time. So you can't use more than a few figures, more than a few words. So those are kind of 2 examples of scientific papers. I put some scientific papers in Blackboard. If you don't have anything, if you do have something, please let me know. But I do want the PDF of the actual paper. And then you write the why, the how, and the what, and whether or not you were convinced in a few pages. I'm being vague on purpose here because some people are like, yeah, I'd like to actually show the entire figure and like lots of other stuff. So it's like, I don't want to limit you. But if you're done in 2 pages, I'm perfectly happy. So, okay. I'll hopefully see you on Tuesday, and I'll hopefully get an email from all of you like, this is the paper I would like to get. Yeah? Okay? Cool. Fantastic, everyone. Yo. If you're done, you're done. Absolutely. No, I am happy with, I try to turn my work in early so that people can just, get on with their lives. That's fine. Absolutely. You don't have to, by the way. Absolutely last minute, although I don't recommend writing last minute. I'm bad at it. I'm terrible at it. But some people need that, 1 a.m. inspiration. Fine, sure.